Okay, so we talked about voltage. It's a very important concept. And voltage, you have to remember, is a property of 2 points. Okay, so it's a energy of 1 coulomb relative to some reference level.
So I came up with what do you test makeup?
Astronomy?
Yeah.
Sit there. Okay, so it's a property of 2 points. So for example, here you have a 12-volt battery. That means from the positive terminal, each coulomb of charge has an energy of 12 joule relative to the negative terminal. So it's always 2 points. Okay, so usually when we're going to find the voltage of a single charge, okay, so a point charge. So if you have just a point charge, so this is my point charge here. Okay, and I can find the voltage. So here you have very high voltage close to it. And then as you move away, the voltage is going to decrease, goes to 0. So at infinity, the voltage goes to 0. Okay, so that will be the voltage of a single point. You see, this is going to be infinity. Very far away is going to be 0. But when you say 21 volt, okay, that will be 21 volt relative to infinity. And what's the meaning of that? It means that if you take 1 coulomb of charge, okay, it does not want to go this way. It's being pushed away. So you have to take that charge in your hand and you have to push it and push it against its will. Push it, go up the potential, higher the potential, higher. So it's like going up the hill. So at that point, this charge of 1 coulomb, we have an energy of 20.8 joule relative to infinity. So it has potential energy stored into the electric field. Now, if you let go, the electric field is going to push it away to decrease its potential energy. Is that clear? So you see that the electric field here is always showing you the direction of the steepest slope. Okay, so it's always perpendicular to the equipotential. So this is a equipotential. It's like a contour line. So typical question, like conceptual question, if I take a walk here along the equipotential, I do not have to do walk because I don't have to fight against the electric field. So the electric field is the force that try to lower the potential energy. It's like a restoring force. So when you look at this, you have to think of that as a hill, okay, it's a mountain. Is that clear? So it's potential difference, potential difference or voltage is a property of 2 points. So if instead of having a positive charge, okay, now I take a negative charge. Okay, so I'm going to have a negative charge. And then I'm going to have the opposite. I have a throw. Okay, I have a dip. It's negative potential. It's negative potential and very far away, it's going to be 0. So that potential here is negative 9 volt, okay, relative to infinity. What does it mean? It means that if you take 1 coulomb of charge here, okay, it has, good morning, a negative potential energy relative to infinity. So you have to think of that as a throw, okay, going down. Okay, it's a dip. Okay, so it's a review, and I'm going to go back to this, but you see here the electric field is always perpendicular to the equipotential, and that's going to be the force that wants to lower the potential energy. So it's trying to bring that positive 1 coulomb of charge lower potential. Positive charge wants to go low potential. Negative charge wants to go high potential, high voltage. Okay? So again, voltage is a property of 2 points. And I think, I don't know if it's in the pop quiz, but in one pop quiz, maybe it's in that pop quiz, I'm going to ask you about an outlet. Okay? So the outlet that we have here, you see you have the hot wire, and then you have the return path here, which is connected to the ground, and this is the ground. Hot wire, okay, that means that 1 coulomb of charge has an energy of 120 joule relative to the ground. So the outlet provides us with 120 volt. Okay, that's a potential difference. It's a property of 2 points again, right? So this is the hot wire, this is return path. Return path is supposed to be connected to the ground. It will at some point, and this is the ground. And you measure that with a voltmeter. So usually I do the demo, but I suppose that you already know this. But here you have your voltmeter. Okay, so on that side here you have direct current. Okay, but on this side you have alternating voltage. So direct voltage, alternating voltage. So the voltage that you get from the outlet follows a sine wave. Okay, it's actually going from 0 to 170 volt, 0 minus 170 volt, 0 170 volt, 0 minus 170 volt. And when you average out, okay, so called the root mean square, you get 120 volt. So let's see if it is true. Maybe that's going to be your last time you see your professor, maybe. So let's see. I'm going into alternating voltage. You agree? Okay, so I have 2 terminals, and here I have an outlet. So I'm going to stick the hot wire into the hot opening here. So this is hot. Okay, stick that into it. If it can go. It cannot go. It was going before. Okay, I cannot do it. So I need someone to hook up. Okay, do you trust her? Do you trust her? Okay, what's your name?
Definitely.
Okay, I'm gonna do it, but I don't want this to be soon. So, do you see I put that in the hot wire? Yes. Hold that. And this is in the neutral path. To agree? And what do you think? 1.1.4. 121.4. Do you trust her? Okay. Did I die? No. Sorry. So you see 121.4, it's about 120 volts. Now the third opening here, it's called the ground, and it's connected to the ground. So it's super safe, right? So I can take a wire like this one, and I can stick it into the ground. I touch it and I don't die. Right? So you can do that to remove all the static on you. It's called grounding. So anyway, if you have a pop quiz question, this is the hot wire, 120 volt, relative to the ground. Do not stick anything into here, but this is safe. So that will be used for people if they do some electronics, and they don't want to have too much static. They can remove the static charges by sticking something in there and touching it. Okay. So now you know. And another thing I want to get back to, slide 23. Maybe I was not clear enough here, but you see, when you go from A to B, at the beginning here, the electric field is equally spaced. So it's a uniform electric field, but it's the same electric field here and the same electric field there because the space between the lines are the same. As you move from A to B, the electric field here does not change, which means it's uniform. Okay, and the voltage will be just equals to the change, the voltage, right? Delta V will be just equals to E times that distance here. Okay, so you go upstream, so you have to go do work on 1 coulomb of charge to go from A to B. Okay, that work that you have to do on 1 coulomb of charge is called the voltage. Okay, so it works like gravity, right? You are going uphill. In this situation here, you see that the lines here are moving away from each other. That means the density gets smaller. That means the electric field gets weaker. It means it takes the same work at the beginning and then it gets easier. In that case, the lines are packed together. So it means same at the beginning and then it gets harder, which means the largest potential will be in that situation C, because at the end you really have to push it against the electric field. So you are doing work against electric field. So you have to imagine that you have a stone in your hand, okay, and you have to go uphill. But this is steeper than this one. This one gets still uphill, but it gets easier. And here it's uniform, right? The steepness does not change. Here it gets less steep, and here it gets steeper. Okay, so I wanted to make sure this is clear. And then what else? Okay, so let's look at your book. It's a very nice book. But by the way, when you study, you should not do like you do for social media. Okay, you don't browse. Browsing doesn't help. What you need to do is to hide the solution and do the problem, like from the assignment, from practice, or from your book on your own without looking at the solution. You have to suffer. You have to pull your hair, right? If you don't suffer, if you don't feel the heat, it doesn't work. Okay? It's not social media. This is not Instagram. You have to hide the solution and do it on your own. Then you have to look back at your notes. You have to look back at the slides. And then finally, if you get stuck, then you can ask ChatGPT or look at the tutorial. Okay? Many students don't know how to study. That's the issue. Blame social media. So anyway, so we define voltage. Okay, it's a scalar function. So that means every point in space you can define a scalar. So this is the voltage for a point charge, one single charge, and the voltage again is relative to infinity in that case. Now you can look at your book. You go back and you can see how they derive it. Okay, they will have to find the work done from infinity to the charge to bring 1 coulomb of charge close to the positive charge. Okay, so use your book. Okay, blah blah blah. Okay, so you can look at, I think it was 757. Okay, they show you how to do the computation. So they show you how to find the work. So here you have a positive charge Q. How much work you have to do to push 1 coulomb of charge uphill. You have to push, you're doing work against the electric field. It doesn't want to go uphill. It wants to decrease its potential energy. And doing so, you do integral. This is the force here, 1 over r squared. When you take the integral, you have 1 over r. That's how you can check. Okay, so the potential derives from the electric field. 1 over r squared, you take the integral, you're going to have 1 over r. So a little bit of calculus. Is that clear? So let's potential energy here. Oh, I wanted to show you something cool also. Maybe it will save your life. You never know. So you see, when you have a hot wire, so those wires from those hot lines, the hot lines, okay, they are not insulated, they are bare. Because it would cost too much money to insulate them, okay? So they are just bare. So if you touch them and you touch the ground, there is a huge potential difference and you will be electrocuted. That's 100,000 volt, a lot of pressure pushing the charge, and they go back to ground. Remember, the ground is the return path to go back to base. So if you have a situation like this, or if you have a wire after a, I don't know, thunderstorm or something like this touching the ground, into the ground, you're going to have equipotential. Okay, so if you stand this way, you're going to be electrocuted because you're going to have a voltage between the 2 feet or potential difference. So they teach you in construction that you have to bring your feet together, right? So if you bring your feet together, now the 2 feet are at the same potential and you're safe. Because if there is no voltage, there is no voltage difference, the charge cannot flow. So you can find video online where you see people, one get electrocuted and the other one has to stand on one foot, which is very hard, or jump on 2 foot, or you have to face the machine here, be on the equipotential, and you won't be electrocuted. So I don't know what it's called in English, but that's French. French. So you see, this is bad because 2 points here. This is bad, 2 points, and she's okay. I don't know why it's the girl who is okay, but she's okay. Okay. Where did we stop? Here. So we did that. So again, you have the potential of a point charge. You can look at your book and you see that's going to be the equation. The potential is relative to infinity. Okay, it goes as 1 over the distance. Okay, so as you go away, the potential is going to decrease. When the distance goes to infinity, the potential is going to decrease to infinity. So if you want to visualize that, you have to think of like a hill, like something like this. Okay, this is your point charge. As you move away, the potential is going to decrease as 1 over r. So it's useful to think of potential like altitude. A positive charge wants to go down because it's like gravity, okay, pulling down a mass downhill. Electric field wants to pull that charge downhill because it's a restoring force. If you have a negative charge, then it's going to be the opposite. Here you have a negative charge, right? So the potential is going to be negative. A positive charge wants to go down. Okay, it wants to go this way because plus and minus attract. If you have a negative, it's going to go up the potential. Positive down the potential, negative up the potential. Okay, isn't that cool? So we already talked about that. So again, if you have, for example, capacitors, so you have 2 plates. One is positively charged, the other one is negatively charged because you connect it to a power supply, like a defibrillator, for example. Defibrillator is 100 volt. So this here will be 100 volt relative to this one. And then the voltage is going to decrease at a constant rate because the electric field is uniform. So the electric field is the slope of the voltage, the greatest slope at a given point. So we say the electric field derives from a potential. It's the derivative. Derivative means steepness. Okay. So if you have, for example, this situation, which is a conductor, So what's going to happen? I'm going to explain maybe with the next slide. But you see, inside the conductor, can you have an electric field? No electric field, right? Electric field equals 0. Can we have a charge inside? No, right? So if you are very far away, okay, you have to push, and it's very hard because you have to do work against the electric field, and it's very tiring, and the potential is going to increase. Do you have to do work when you go inside? No, because there is no more electric field to fight with you. It's only electric field fighting. So inside here, the potential is not going to change. So the electric field will be 0 inside, and then it's going to be on the surface. There is an equation for that, and then the electric field goes 1 over r squared, but the potential is going to be constant inside on the surface, and then it's going to decrease as 1 over r, because inside you are not fighting anymore against the electric field. Okay? So there is no electric field inside. You have an electric field going this way, it's like an aura. So if you remember the electric field as a function on the distance, there is no electric field inside. And all of a sudden you have something like this, 1 over r squared. Now close to the surface, the magnitude is sigma over epsilon 0. If you use Gauss law, and inside here the electric field equals 0. Okay, but the potential is going to be constant. So if you look at this girl, she's isolated. Okay, she's isolated from the ground, so she's safe. She's not going to be shocked. And you see here, she is at the same potential, maybe 100,000 volts. It's not the potential that will kill; it's the current. The charges are pushed by a difference in potential. If there is no difference in potential, the charges will not move. So she will be safe. And this is an equipotential, this is an equipotential. Okay? You see the voltage always wants to go to the ground, you see? So that's very bad. Far away you're fine, but you should not make step toward it, right? Because electricity wants to go to the ground because that's where the return path is connected to the ground. A lot of fun.
Helen, we are 2021 and all of my students are getting.
So you see, are they shocked? No, because they are isolated. They don't touch the ground. They will be at the same potential, 100,000 volt. But if someone comes and that person is connected to the ground, what's going to happen? All of them are going to be shocked, right? Are they going to die? No, because you don't have enough charges on a Van Graaff generator because the capacity is very low, cannot hold many charges.
Holding hands and they just love each other so much. Oh wait, no. Josh is holding us at a 500,000 volt charge. And now Mark's hair is starting to go. It's going to give him a fist bump. Everybody's going to be so happy. So whenever you are ready, go. Ladies and gentlemen, here we are.
It's very unpleasant, but it's not deadly, okay? Unless you have a pacemaker, so don't do it in that case. Okay, so that will be the equation for voltage. You see, inside the Van Graaff generator, there is no the potential. It's an equipotential. inside on the surface it's going to be the same potential, and then it goes 1 over r. That will be the calculus here. We already talked about that. It means that's going to be the definition of the potential, right? How much work you have to do against the electric field, okay, to increase the potential. There is a negative. Negative means that the electric field wants to lower the potential energy. It's a restoring force. So it's like a spring that you try to stretch. There will be a restoring force. And you have to use calculus. Okay. So for example, here, okay, let's try to do this. So what's going to be the potential at 1.2 meters away from that positive charge? Relative to infinity. So you just use the equation, right? If you look at your, you see here, the voltage of a point charge is kq over r. So you just plug in. So the potential here at that point, okay, it's going to be K. So 9 times 10 to the 9. The charge, which is 4 times 10 to the negative 8. And then over the distance. So imagine here you have that potential here. That means the energy for 1 coulomb of charge that you bring from very far away. So 1.2. So what you get? 300 volt. Okay, so that will be the work that you have to do to work to push against the electric field and to bring it here. If you put a positive charge here, it's going to accelerate, right? It has potential energy. It's uphill. It doesn't like to be uphill. It doesn't like to be here. It wants to go back downhill. Now, if here you have a negative charge, okay, negative charge, you're going to have a negative potential. Okay, so now it's happy because it's positive, this is negative, and it's saying, oh, cool, right? See, that's going to be a negative potential. So it's same thing, times 10 to the 9, but now we have a negative 1.2, you get minus 100 volt. Okay, so why is it negative? Why is it negative? That means it's binding. So each time, that's important in chemistry. In chemistry, because when you have a negative energy, that means it's binding. So all the molecules, all the the atoms inside the molecule, they have negative energy. That means they are bound together to make the molecule. If you try, did you put your name and everything? Yeah. Okay. Ah, no. Oh no, you're gonna make me walk too much. No. Here. All right. Thank you. And what else? Yes, so if a molecule, all those atoms have negative energy, that means that you have to do work to break it, Okay. Okay. If you place a positive charge here, what's going to happen? It's going to go down. Down. Okay, down the potential, so away from the positive. But if you put a negative charge, it will want to go up. Yeah, up the potential. Very good, right? Negative goes up the potential, positive goes down the potential. Okay, so let's try to do this one. So this is called a distribution of charges. And what do we want? We want the voltage at A and the voltage at B. So it's going to be easier than for the electric field because it's not a vector, it's a scalar. So you just have to add numbers. Okay, you don't have to worry about the cosine and the sine, x component, y component. By Pythagorean theorem and direction, you just add numbers. Okay, so this is called the distribution of charges. So at point A, okay, it's gonna be K, and then you have the charge. The distance is 0.2, and then don't forget the minus here. K, 8 times 10 negative 9, and that will be 0.6. Okay, so the potential will be K times 10 to the negative 9. Thank you. Okay. You are the only one who show up, so good for you. 0.2 minus 0.1 over 0.6. Okay, so it's gonna be what? Yeah, 240 volts. You see, it's positive, so it means it's not happy. Okay, it's not binding. It wants to get out of the here. Okay, it's not happy to be here. It wants to go toward the minus. So it's a potential energy. It's a positive potential energy. It's not happy here. Yes.
Sorry. For the makeup, take it in class or give me afterwards.
The makeup, it's after the class. No, after the class, because that's why it's quiet. You talking about astronomy? No, no, this class, right? Yeah, yeah.
Oh, he was taking
Yeah, he was taking astronomy. No. He was taking astronomy class. Oh, which is a very easy class. But I have very bad students. So. Okay, what about the potential at B? In astronomy, okay, not here. What's going to be the potential at B? 0. Okay. So you see, it's much easier. Electric field is hard because you have to deal with so now if you have two charges, you have a dipole. Okay, let's say this is 180 volt, you have a positive charge, and at the top here you have 180 volt. Maybe it's something flat. And here you have one minus 180 volt. What's going to be the potential between them? So between 180, so sorry, this is 0, you have 180, and you have minus 180. If you go from minus 180, you have to climb. What's going to be the altitude, the difference in height? Exactly, is that 360? Okay, that's a mistake. 360 volts. Okay, so again, voltage is a property of 2 points. So that means if I take 1 coulomb of charge in my pocket and I go uphill and I have to fight against the electric field, the work done, okay, that I have to do will be 360 joule per coulomb. Okay, so if you take I'm skipping. I don't know where is my slide. Oh, I'm lost. But if you take the outlet, so this is 120 volt relative to this one, but then you have the 240 volt. You see, if you have the big outlet for the laundry machine or the dryer, so they consume a lot of energy, but you don't want to provide too much current, right? Because the fuse will break. So what you do, one is at minus 120, the other one here is at 120. So what can be the voltage? 240 volts. Okay, so that way, because any machine, any devices that has a motor inside is very, very demanding in energy. To increase the energy, you can increase the current or the voltage. You don't want to increase the current too much because the maximum is about 20 amps in a house, so you increase the voltage instead. So what you do, you use two sine wave, okay, because remember, the voltage here follows a sine wave. You take them out of phase. They're out of phase. So one goes to the crest, the other one goes to the throat. So you have 120 minus 120, that will be 240. That's how you can provide enough energy to the dryer. And this is safety because that will be connected to the ground. So if you touch the device, hopefully it won't go for you. If there is a short, it will go to the ground. Okay, so that's how it works. Okay. Okay, so what do I need to do? Here it says go to the textbook. So you have a positive. No, I have to do something else before. Okay, let's go back to the dipole. Okay, let's take a dipole. You have a plus here. I'm gonna take a plus here. I'm gonna take a minus. They both have the same charge. Okay, and can you try to draw the potential? What it looks like? Okay, you're gonna have a heel here, and that is going to be a negative potential. Just on your notebook, try to draw what it will look like. Okay, so very far away, it's going to be, see, it's going to be positive infinity, very far away, and then it's going to increase. So you are going uphill, uphill, uphill. So if it's a Van Graaff generator, you're going to go to 100,000 volts. Here it will be, in theory, infinity. And then you go downhill. See, downhill. And you go downhill. Okay, downhill. And then you go to negative infinity. Okay, that's going to be a pop quiz for next time. So pay attention. So it's going to be here negative. So try to draw it on your notebook on 2D. So it means you're going to have something like this, right? You're going to have, this is the x-axis here. You have one charge here, which is positive, and you have one charge here, which is negative. And the y-axis is going to be the potential. Okay, that's going to be my potential. So very far away from the plus, it's going to be 0, but 0, it's not positive, 0 plus if you want. Okay, it's going to be positive, but going to 0. Okay, it's what we call that, a limit, right? So here it's going to go up, 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 very high. Okay, and what's going to happen in between? Yeah, it's going to go to 0. The potential will be equal to 0, right? So you're going to go something like this. And then, without doing the math, you should do something like this. And now it goes to minus, 0 minus. Okay? So that will be the potential around a dipole. Here it's going to be 0. Here it's going to be 0, but below the x-axis. and in between you're going to have a positive potential. In between you have a zero potential. Okay, zero potential. Which means if you have 1 coulomb of charge here, it has no energy. You see that the electric field is always perpendicular to the equipotential. The electric field is showing the direction of the steepest slope. How to go downhill the fastest. Okay, so if you have a positive charge, it's going to be pushed away, and the electric field is showing pushing away, right? To go downhill. It's always going downhill, downhill, downhill. Is that clear? So if you do it in 3D, and you can do that with Python, for example, okay, you have a dipole, it will look like this. So you have the electric field lines here, positive and then negative. A positive charge wants to go down the potential, negative charge wants to go up the potential. Isn't that cool? Okay, so this one is from the book. So I'm not going to go into details because the book is easy to get. It's very cheap if you know how to get it. 765. Okay. So for example, if you want to find the potential at point A, how you will do that? You just add the potential from Q1 and then the potential from Q2. Do you agree? So you can see, you can do the math quickly. Okay, you can factor out and the K, and you will get minus 900 volt, which means it's binding. It means if you want to remove 1 coulomb of charge, or if you want to remove a positive charge, you have to do work. Okay, so that means that if you have 1 coulomb of charge here, its energy will be negative 900 joule. If you have a Q charge, a charge Q, you just multiply by Q. Okay, because potential energy is the voltage times Q. Okay? Because the voltage is for 1 coulomb. Okay, so the potential of energy here of 1 coulomb, it's going to be 900 joule. It's negative. If you place a positive Q charge, the potential energy relative to very far away equals Q times the voltage. So it will have a potential energy of negative potential energy. It's binding. So if you pin a positive charge there and you want to remove it, you have to do some work. Okay, so same thing with water. If you do electrolysis, and if you want to split hydrogen from oxygen, you have to do work because they are bound together. Okay, so you have to put 2 electrodes in water, bring electric energy, and split oxygen from hydrogen. So if it's negative, it means it's bound together. Okay. Now for B, that point B, positive. So what do you think? Just with your guts. If you have a positive charge here, and it's far from negative charge, but it's close to the positive charge, is it happy? No, right? It's going to be pushed away. So the voltage will be, the voltage at B will be positive. It will be positive, okay? Because it's going to be pushed away. It's not bound. It's not happy. It's going to feel a force. Get away. I don't like you, okay? Positive and positive, they don't like each other. You have some minus, but that's not enough. The plus here is closer. So the voltage will be positive relative to infinity. And I lost the page. What was the page? 765. Do you see where is the computation at B? So at B, it's going to be 1030 volts. I don't know, the computation is somewhere. Okay, at the other point, it's going to be, no, it's not there. But it's easy to compute, right? Okay. Oh, what about C? What do you think the potential is at C? Zero, very good. The potential is going to be zero, right? Because the distance from the plus and the distance from the minus is cancel each other. So that means if you place a charge here, it's going to stay. It's not going to move. Okay, so now you can do the computation. Have fun here. If you have a dipole, positive and negative, and you want to find the potential at P, okay, you can do the math here, and you can even find the potential at a very, very large distance. So remember, when we work with dipoles, usually they are molecules, right? So the distance between the two nuclei is very small. So we introduce a new physical quantity, the dipole moment, and we say it's very far away. We are looking at a point very, very far away from the dipole. If you do the computation at a very, very large distance, that's what you're going to get. It's 1 over r squared. So remember for the test one, I think, or a pop quiz, do you remember the electric field far away from a dipole? It depends on 1 over r cubed. Very good. Okay. And if you take r cubed, 1 over r cubed, and you take the integral, you have to take the integral, right? No, the electric field they have, so the voltage, you have to take the integral, you're going to get 1 over r squared. So it means you have the voltage and you have the electric field. If you want to go from the voltage to the electric field, you have to take the derivative. And if you go from the electric field to the voltage, you have to go and take the integral. So this is 1 over r cubed. That's going to be 1 over r squared, very far away. So the electric field derives from the voltage. You are taking the slope, and to get the voltage from the electric field, you take the integral. So the integral of 1 over r cubed is going to be something in 1 over r squared, except it's complicated because this is a scalar and the electric field is a vector. So we need some kind from calculus 3 or calculus 4, or I mean it's called vector calculus. We need a tool that will, for us, that will take you from, for example, from a scalar to a vector. And that will be called the gradient. So that's, you don't have to worry about that. Just if you're taking calculus, you have to take vector calculus if you're an engineer, but you see the electric field will be equals to minus the gradient of the voltage. This operator here, it's called the gradient. If it's in 1D, then you say the electric field is just the derivative of the voltage with a minus for the x component. And then when you pack all the components together, you're gonna get that. For those who are taking calculus. Now if you are not taking calculus, it's very simple. It just means that the electric field is the slope of the voltage. Is the largest slope. The electric field is just the slope of the voltage. Okay, so what do you, so definitively on the next pop quiz, so here it's a little bit more tricky. It's not a dipole. You have 2 plus and 1 minus. Agree? So it's like you have 2. So 1 and 1 is 2. And here you have minus 1. The goal is for you to trace the potential. Try to trace the potential, what it will look like. See, because from very far away, 2 minus 1 is what? 1. So everything happens from very, very far away, that you just have one positive charge. So the voltage should be positive, above 0. But very close, here you have a hill, and here you have a throw. Okay? So try to trace that on the x-axis. So very far away, it's going to be a positive charge. Very far away, you know, you don't have the resolution. Everything's merged together. You just have one positive charge. So the voltage will be positive. But very close, here you're going to have a hill, and here you have the throw. So don't stare. Do it. So on the x-axis here, so this is, you have 2q, and here you have minus q. So from very far away, the potential is going to be positive here, above. So 0 plus here and 0 plus there. Is that right? Because from very far away, it's like a positive charge. As you get closer to here, you're going to go uphill. It's very steep here, and then it's going to be very steep there. Okay, now this one is going to be downhill, but not as much as that. So it's not going to be as steep. So it's going to do something like this. Okay, and then you have to go above again. You see? So how many places where the potential is going to be 0? 2, very good. You're going to have 2 places. And then you can do the math and find those places here. So that will be the distance d. Is that clear? Now you can show that here. I can take 2 plus, and I can take only 1 minus here. Now very far away, it's going to be positive. And above, and very far away here, it's going to be weird, but it's going to be positive as well. As you get close to the negative, we're going to have negative potential because it's going downhill. It's going to be downhill, right? Downhill. And as you move closer to the positive, it's going to be uphill, uphill, uphill. So you can show here is minus. You see, you're going to have 2 places where the potential is going to be 0, somewhere there and somewhere in between. Okay, you can even you can play with it and show the ratio of the distances. Okay. Now, if you do the computation, if you want to find this place, let's call that place X. Can you find that place X? So at that point, at the point A, you see, the potential equals 0. try to find x. And the as a term of d in terms. This is very uncomfortable. Mhm. So at point A, the potential equals to 0. Not 1/2 because this one is larger. 2. Here you have 2q. You are right if it's a dipole. If you have q and minus q, that's going to be d over 2. And yes, you can do it in your head. So it's going to be closer to this one than it is from that one. So my drawing is not great, right? So you're going to do from this one, it's going to be 2. Let's say the charge is, let's forget about the charge. Let's forget about K. I mean, you can do, okay, let's do K. Okay, let's do K. So from this one, it's going to be, what's the distance here? X, right? Minus Q, K. What's the distance here? Between here and there. Yeah, very good. T minus X equals 0. Okay, so this is simple algebra. You can factor out here 2x minus 1 over d minus x equals 0. Okay, so you have what? 2 over x equals 1 over d minus x. So what do you have? 2d minus 2x equals x. Huh? So x equals 2/3. Okay, so it's going to be more, one, oh, not bad. Okay, 2/3. This is 2/3. Okay. No, because this one is going to take, it's stronger than that one. It's going to go reach 0 at a farther distance. Is that clear? Yes or no?
Yes.
Okay. Let's look here. So it should be somewhere close to here, right? So 1, 2, 3 should be somewhere there, and here you have a 0 point something. Okay, try to do this one, the other point B. Okay, do it yourself. So in that case, I'm going to call this is X now. Is that X? Yes, this is X. At point B. So point B equals 0. So from here, it's just going to be X. Is that right? So it's going to be 2kq over X minus kq over, what's the distance? X minus d, right? Equals 0, right? So it's going to be kq 2 over x minus 1 over x minus d. Okay, let me know what you get. Equals 0, right? And you get what? X equals mm, x equals what? Hello, how you doing? X equals X equals 2x equals 1 over x minus d. You cross multiply 2x minus 2d equals x. 2d, this is a d. So you bring this one here, so x equals 2d. Okay, so it will be at the location twice as far. Is that clear? Okay, you play with it, right? So it means the location for the next 0 will be that distance here multiplied by 2. And you see here, it should be about there. 1 distance, 2 distance. You have 2 0. This is 1 0, and somewhere here that's another 0. Okay? It's just, you can play with that. So that's for the next pop quiz. Uh, okay, so that's the question here. So this comes from an algebra-based book. And conceptual question, how many 0 voltage do you have? You have 2. One is here, one is there. That distance here is 2/3 of the distance between the charges, and this distance here is twice this distance. Okay? Any question? And then you can have very cool configuration. So this is a distribution of charges. And you see, it's like contour lines. You have contour lines, right? So it's like you are looking at a map. You are going hiking. So this is uphill and then it goes downhill. Here you have a downhill here. In between, you're going to have a 0. Okay, so you can have the contour lines. The electric field is always perpendicular to the contour line, to the voltage, okay? Equipotential, always perpendicular to the equipotential, and the electric field is a slope, is the largest slope. If you take vector calculus, the largest slope of a function is called the gradient. It's an operator. Okay, so again, you have different configurations here. So if you have something sharp, the electric field is always the strongest because you're going to have a very large density of charge. Okay? So the equipotential here will be very close to each other. Here, positive and positive, you have negative, negative. So you have different configuration. So if you have a point charge, what will it be, A or B? So when the contour lines are close to each other, that means the steepest slope. You know that when you go hiking, when you see the contour lines close to each other, you say, oh, this is trouble. Or this is good if you like workout. It depends. Okay, I'm trying to avoid the steeper. But if you like working out, of course, you're going to choose this one. So the answer will be A, right? You go from steep, very steep, and then it goes 1 over r, gets easier and easier and easier. So that will be the equipotential with a positive charge. Very steep, the equipotential are closer to each other, and then it gets easier. So it works like this, right? When you see those lines very close to each other, it's going to be very steep. It's going to be very hard to hike. If the equipotential are farther away from each other, it's going to be easy to hike. Agree? Okay, so here you have equipotential. You go from this point to this point. Are you doing any work? No, very good. You are on the same level. You don't have to do work against gravity. Same thing, you don't have to work against the electric field. You go from V1 to V2. So from 100 volt to 90 volt. Okay. So in that case, you see you are losing potential energy. Okay. So it's the electric field doing work on you, right? You are losing. The work that you are doing is negative because potential energy is decreasing. If you go from here to there, is it going to be the same amount of work? Negative work. Yes, because it's not path dependent. Okay, electric field is conservative. Doesn't matter which way you go, as long as you go from 1 to 2, what matters is the 2 points. If you go from here to there, is there any work done? No, very good. If you go up the potential, positive work. If you go down the potential, negative work. Up the potential, you have to work against gravity, you have to work against the electric field. Okay, so a lot of application in the medical field, for example, the heart, and I forgot how it works, but it has to do with sodium going in and going out, so polarization, because charges are moving in and out. You're going to have a positive potential and then you have a negative potential. So it's a dipole. And then it's going to be polarization, depolarization, polarization, and then it gets complicated and I understand nothing after that. But you see that you have potential, difference in potential. Okay, so it's always potential between D and E, A and B, B and C. Don't ask me for the details, but that's the idea, right? So that's why we need sodium. Without sodium, we cannot have this potential difference. So again, some calculus here, nothing to be afraid of. You see, the electric field derives from a potential. So any restoring force derives from a potential. It's a restoring force because it wants to lower the potential energy. And that's called the gradient in mathematics. And it's super complicated when you have to do spherical coordinates, cylindrical coordinates. It's a headache. But you don't have to worry about that. You see, the gradient, okay, is just a way, it's a mathematical tool that we have to find the steepest slope. Okay, so you have the voltage. The voltage is a function, is a scalar function. It's a property of space. Every single point here, you're going to have a voltage. To find the electric field, you will find the slope at that point. Okay, so typical conceptual question about the slope. The electric field is the slope of the voltage, but it's showing you which way, which direction the potential will decrease the most. Are you with me? You don't space out? Don't space out. A little bit math. Mathematics. So for example, here you have a function in 3D. That's a function, okay? I'm not going to ask you to do that because I don't know how to do it without using Wolfram Alpha, but just to understand the concept. This is a function in 2D and 3D, okay? That will be the equation here. When you're going to find the gradient, what you are finding is just the slope at every single point. What's the slope here? What's the slope here? What's the slope here? That's going to be the gradient. And the gradient will be the electric field. Okay? So, for example, if you have a parabola in 3D, so Wolfram Alpha, so just to connect to math, so you see why math has been invented, is just to serve physics, obviously. So plot x square, you know, because Newton invented calculus. For what? For physics. So I don't know what, do you know the name of that? It's a paraboloid. Paraboloid. That's a parabola. It's a hammock. And if you take the gradient, plot the gradient, see if it works. Okay, you're going to find the slope. Okay, so very large slope at the center, and then the small slope at the center here. Can we do both? I don't know. Oh, it doesn't want to do. And plot maybe. No, but you see what it did, right? It computed the slope for every single point. No, I don't want to pay. Okay. So for example, here you have the voltage as a function of distance. So this is 1D. What do you think the electric field is? What is the electric field? The electric field is the slope. So what's going to be the slope? Huh? -2. Okay, so the slope, okay, is the change in y over the change in x, rise over run. So it's going to be 20 volt over 10 centimeter. That's going to be the magnitude of the electric field. So it's going to be 2 volt per centimeter. So it means that the voltage, okay, is going to change by 2 volt for 1 centimeter step. Okay, so for example, if it was the plate of a capacitor, that will be positive here, that will be negative there. This is connected to the ground. This is your 20 volt. So you have a power supply here, it's connected here. See, the electric field goes in this direction, and the potential, the equipotential goes from 20, and every centimeter is going to lose 2. Okay, so 2 centimeter, that will be 18. Okay, another centimeter is going to be 16, and blah, 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 and blah, 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 and blah, 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 and you get to 0 volt. Okay? So it's the slope. Okay, so let's try to do this one again. Electric field is the slope. And these are equipotential, which are like contour lines. Where is it that the slope is the steepest? Where is it that if you love workout, where is it that you want to hang out, to chill out? 5, right? Exactly. That will be the steepest slope. You go from 40 to all the way to 0. So going this way is going to be the hardest, but going that way is going to be easier. So if it was me, I would go that way, and then I go this to get to the summit, so it's easier for my knees. So property of 2 points. So this here is the steepest, right? So the electric field is the derivative, so change of voltage over the change in distance. So you go from 40 kilovolt, so 40 kilovolt minus 30 kilovolt. So that will be your rise over run. It's a step of what? A meter, 1 meter. Okay, so that will be 30 kilovolt per meters. So you are 10. So you are losing 10,000 volt for a step of 1 meter. The electric field, again, is the steepest slope. So you're going to have a electric field will be in this direction, showing which way to go to get downhill the fastest. So it's like when you have water going downhill, it's always choosing the best path to go down the quickest. So it's like water flowing. Are we okay? Not easy, huh? Trying to make it as it's not easy concept. Okay, so for example, here, if you have when it's something is sharp, we have seen that's where you're gonna have the largest density when it's a conductor to make sure that the electric field equals to 0 here. So that means the electric field here is very strong. Okay, that means that the contour lines are very close to each other. Okay, it's going to go down very quickly, so very strong electric field. It means you get very close to a chance of breakdown. If you have a conductor in air like this, here you have at the hot lines, this is bad because this is a coronal discharge, because the electric field is so strong, because you have a sharp edge that you have a breakdown, which means that you have reached 3 million volt per meter. Once you reach 3 million volt per meter, that means there is a breakdown. What does it mean? It means there is a discharge. What does it mean? It means that the electric field wins and is able to pull those positive charge and to bring them, trying to bring them down the ground. Okay, and the air gets ionized. So this is called a coronal discharge, and it's an issue because each time you have a coronal discharge, you are losing energy. So bad engineering means you are losing too much energy here. It's not good, right? Because you're losing money. Losing energy is like losing money for the people making those lines, right? The power company, whatever. We'll do that computation next time. Van Graaff generator again. And because it's 10:49, and then it's the joy of calculus again. So I gave